Let us look at conflict clause optimizations. So far we have seen that we have a conflict, we draw the implication graph and then learn conflict clause from them. However, we will see that there are more than one choices we can make with respect to conflict clauses, and there are some desirable properties. Let's look at what kind of conflict clauses we like to have. If a conflict clause is smaller, it prunes away more such space, which we can understand by this example. Let's suppose you have three variables in your formula P, Q, and R, and if we learn this conflict clause P or Q or R, we can easily see there's only one assignment, which P equals to 0, Q equals to 0, and R equals to 0. That is actually unsatisfying assignment. So it rejects only one assignment. Let's suppose we have a P or Q as a conflict clause, so it basically rejects two assignments. Similarly, if you have a single literal conflict clause, it will reject 4 assignments. Secondly, there is some idea of a center of action. When you make a decision, it's not necessary that variable is very important for the formula such that you quickly find contradictions or get a satisfying assignment. So you want to find those variables that are some sense important. You need some way of analyzing the conflict graph, so then you can say, oh, this particular literal seems to be far more important than the decision variables, and we will see both of these needs will come together in the optimization we'll just see. We introduce a concept of cut clauses. What is a cut clause? Let's read the definition. Consider a cut of an implication graph that separates the decision nodes from the conflict node. Let L1 to Lk be the literals that occur at that cut boundary. The cut clause for the cut is disjunction of their negation. Very mouthful definition. Let's look at an example. So let's look at this example, which we have drawn in our running example. So in this example, you just cut somewhere. Cut this graph such that decisions are separated from the conflict. Okay, so let's look at this cut. So in this cut, you have two literals which are at the boundary, this guy and this guy. What I will do, I will take the negation of this literal here and the negation of this literal here and take the disjunction, and I will call it the cut clause. You may be wondering why I want to define something like a cut clause. Very easy observation. Just look at the graph from the cut. Okay, just look at this piece of graph. Okay, ignore this node and this node. You will find this, it exactly looks like implication graph. If I had made these decisions not of P5 and P1, I would have get the exactly same implication graph. Therefore, you can treat them as decisions and make a conflict clause out of those decisions. Very simple idea. So you may be wondering, I can cut anywhere. So any cut would produce a conflict clause. So you can choose. You are free to choose any cut. So there will be choices. So you can choose one cut or another. Some cuts will give you a very long clause. Some cuts will give you a very short clause. So you want to find a cut which gives you a short clause, and that becomes an optimization step in learning conflict clauses. So now the question comes, how to efficiently find the cuts that are small? And there have been various proposals. So one of the proposals is called unique implication points, and I will define what are those. And any cut involving those points guaranteed to be short. So what is a unique implication point? In an implication graph, a node at level D, okay, is a unique implication point at decision level D. Basically both are D, so they are same decision levels. If LD occurs in each path from Dth decision literal to the conflict. Consider the following implication graph. in this graph, I have dropped the clauses, and actually just by looking at the implication graph, you can reconstruct that which node is due to which clause. So it's not that difficult to see. So let's start assigning implication points at the level 1. What are the implication points at level 1? So well, every path from decision level 1 goes via this decision, because the decision itself should be an implication point. Every path from here, every path goes. And you can also see Q also is a candidate. It's every path from P to conflict goes through Q. However, the R is not a candidate for UIP. Similarly, you can learn implication points for V. So it goes V, W, and X is not a unique implication point for V because it's a different level, but it occurs in all paths. So this guy is not. Okay. Let's carry on, and for the decision level 3, you have implication point TXT at 3 and X. Okay. So both of them satisfies the definition. Okay, so what is my first UIP strategy? So what do? We iteratively replace a decision literal by one of its UIP in the conflict clause. Okay? And preferably choose UIP that is closest to the conflict. So every level we saw there were several UIP points. So what do? You have initially you had the cut. Slowly you move for all the decisions. Cut that you will find closest to the conflict will be your the cut learned via the first UIP strategy. Let's look at in this example how this proceeds. Okay, so first you have this cut. Okay, it learns this conflict clause, which we have. This is our traditional conflict clause when we learn via implication graph. Then our strategy says take a decision level and move your cut forward. So what did we do? What we said, we will replace. It's arbitrary choice. You can start anywhere. You can start with the first decision, second decision, third decision. So what we decided to move my node from V to W, and then I get this red cut, and then you get this conflict clause. Now I decided to replace T and W with X, and then by great luck, this W disappears. Okay? So one important observation to understand this first UIP strategy is that it always produces smaller clauses as compared to the initial clause, because each time you take a node and when you move forward your cut, you replace it by the unique implication point, and since it's a unique implication point, it guarantees that the cut either reduces or remains the same. Therefore, UIP allows me to keep the length of my clauses short, and in a very easy and effective way to find the new cuts. And then the first means you try to get as close as the conflict, and therefore you are much closer to the action. Once you learn this cut clauses, so you lose information. You lose this information that you made some decisions, some variable got assigned, and then they caused finally the conflict. You remember that for how your cut causes the conflict, but how the cut was arrived at, you lose that information. There's a way to retain that information, which we'll call back UIP clauses. It records the relation between the original decision variables and the nodes that are at the cut. Okay. For example, in this green cut, the T and V were replaced by X. So now you need to remember the relation between that between T, V, and X. That by setting T and V true, X became true. So to record that, you can add this clause in your, which we call black clauses. If V and T are set true, X has to be true. Sometimes some solvers also learn these clauses, not universally. Some solvers have this feature also.